I will be trying to it's fine now. Thank you so much. Yeah, so thank you for giving me the chance to present another interesting work that we've done on RumbleDB, and that is adding scripting with side effects. This work was done in collaboration with Professor Gustavo Alonso and Dr. Ghislain Fourny from ETH Zurich. And without further ado, I'll continue to discuss about RumbleDB, a bit building upon what David presented before. So I'll skip a few details related to more of the intricacies of RumbleDB, and I'll take a more of a practical approach to how these changes can be used, why they are useful, a bit of how we've done it as well, and also some interesting new additions to RumbleDB overall and how that will change the future of it. So I'll just skim through some introduction and background. I'll discuss a bit about the motivation of this work. I'll go through the XQuery scripting specification implementation within RumbleDB. I'll speak about the new additions in RumbleDB, which allows us to basically use functions similar from NumPy and Pandas, but now native in JSONiq. And also discuss a bit some experiments that we've run with these changes and some future work. Now to start, obviously, and ending with some Q&A. Now to start, I guess how David also mentioned before, today's world generates a lot of data every day, and this can come from, you know, a bunch of different sources. We have our social media apps, but also just general logging. If we think about systems on the web, just tracking information and so on, and we have in general quite a lot of different kinds of ways we can store and process this data. And thinking about how much an exabyte is, like that's 10 to the 18 bytes. When we speak about such big sizes of data, one machine is just not enough anymore. So, and what we have to do is to kind of change the paradigm into how we store this data and also how we process it. And to help that, we can think about some standards. We can either try to describe data in terms of some specific key terms like volume relating to how much data we have, velocity relating to how fast it comes in, how fast we can process it, and so on, and the different kinds of variety that the data comes in. And this variety can also kind of stem into the different kind of categorizations that we can have for data, which is having it structured, which is similar to what we can see in relational databases that I guess everyone knows these days. But we can also have it as being unstructured, similar to what something like MongoDB may process, or semi-structured, which is a kind of a mixing where we may provide a sort of schema that can describe the data a little bit, but at the same time not store it in a traditional relational database. So like I just said, in general, the structured data relates to table representations. Unstructured data can also represent things like your text, your image, video files, and other things that don't necessarily adhere to a schema or a specific structure. And semi-structured data is usually going to be represented as three structures, that is using JSON or XML. I guess everyone around here knows about XML, and probably most of you also know about JSON. So David already gave quite a bit of a presentation on JSON, which I'll just skim through. But once we figure out how we want to store the data, that is using JSON or XML or anything else, we also have to think about how we can process the data. And so data analysis is usually going to be done these days using multiple machines, because like I said, data is just so big that it just can't fit on a single device anymore. And for that, the different tools have to be able to interact with data remotely. They have to be able to connect to different servers and possibly fetch data from there or execute instructions there. They also have to make the interaction easier for end users, because otherwise probably no one is going to use a tool if they have to take care of all the networking protocols or synchronizing computations and so on. they also have to handle results in chunks. Like they can't just process exabytes of data and then just send it to a single machine. Probably has to have some interesting and good post-processing mechanisms. It also has to work with different storage systems, and the list just goes on. Now, there are solutions like Apache Spark that resolve part of these issues, but it's not really abstract enough for the general user. I feel like even for me, using Spark requires quite a lot of thinking about how do I want to configure everything, because there are just so many different options. You can connect this with a bunch of different kind of storage systems, and you can use it in various different ways. So what we are trying to do with JSONiq and RumbleDB is basically ease this interaction while still relying on Apache Spark, provide an interface through a language, which is JSONiq. It can basically ease this interaction and relying on RumbleDB to execute queries in a smart way such that users don't have to worry about all this complexity. So like David said, JSONiq is a query language designed for JSON type data. And it provides a SQL-like interaction using a declarative language. As you probably know, an example JSON is usually represented using the curly braces and having key value pairs where the keys are strings and the values can be any sort of atomic type or object type or array type, including themselves other atomic types. And if we were to think about something like JSONiq and how it actually queries, as David gave enough examples before, but in general, it has a very sweet SQL-like declarative approach where you can write instructions using keywords like, for instructions, group bys, returns, and you can even perform operations by calling built-in functions like average in this case, or just relying on user-defined functions. On the other hand, RumbleDB is the query engine for processing large, heterogeneous, and nested collections of JSON data using JSONiq. And what's really innovative about RumbleDB is that it automatically selects how to perform queries. Either they should be done locally if it's something that can fit on your machine and it doesn't actually need the complexity of distributed computing, or doing it distributed. And like I said, it uses JSONiq to ease the interaction. So users can just write queries and then RumbleDB decides how to run it for you. It can handle terabyte ranges of data, and it's always going through new phases of introducing new features and so on. So if anyone is really interested to also learn about potential additions to RumbleDB to also support other data types, XML or other things, I think you should watch out for these changes coming in the future as well. And to give a bit of an example as well into RumbleDB very quickly, as you can see here, there's a query that basically just goes through a sequence of items where we have integers, strings, booleans, and nulls. And what we do is we basically try to group, we basically collect all the entries in here that belong to a specific value. And RumbleDB behind the scenes can rely on Apache Spark without users knowing, which I feel is going to make a lot of users happy about having to forget about how to set up Spark, how to use the API, and so on. Now, to actually get into what this work is about and the motivation behind it, I'll actually have to discuss a bit about the shortcomings of JSONiq. Like I mentioned, it's a declarative language, so sometimes users may actually want to be more explicit in what they want to do. Maybe they are used to performing operations like in normal languages like Python or C++ and so on, and they wouldn't just want to read some JSON, run just a query that groups things by some specific field and then collect some results. Maybe they also want to apply some pre-processing algorithms, or they want to do some explicit kind of sorting and so on. And for that, we actually had to add side effects to RumbleDB and to JSONiq's grammar. So we wanted to extend the capabilities of RumbleDB beyond just querying. We also one with these side effects to allow for things like data to be stored, such that you can actually perform some queries using RumbleDB, and then you can make a request using some external API where you can actually store the results in something like a data lake. We also wanted to allow multiple changes to data to happen if you want to do iterations, things like while loops, so that basically you can have counters and other things happening behind the scenes in a much more straightforward approach. Like I mentioned, we wanted to allow more complex algorithms like sorting. We wanted to also allow more external interactions, and also imperative uses of JSONiq, because I think most of us are used to writing imperative style code. This would also help some users to get more familiar with JSONiq. We also wanted to enrich the analysis capabilities of RumbleDB. So we wanted to add more features when computing things with RDDs, such that you can actually look into specific metrics and so on, but also for data frames, such that you can actually inspect how your rows look, or you can perform null fillings and so on. So to start, we'll just discuss a bit about scripting and side effects. So what I have mentioned so far. What we've done is we've taken the XQuery scripting extension, which maybe some of you might know. It's also been adapted into Zorba for the first time, and we tried to strictly follow this specification when implementing it within JSONiq. What that meant was that we strictly follow the grammar rules and all the other imposed requirements related to making expressions being sequential or non-sequential, meaning sequential refers to side effecting operations, or expressions in this case, and non-sequential being non-side effecting. So what that means is that prior to our changes, everything that JSONiq could do was non-sequential. And now we actually extend the whole world of JSONiq to allow for these sequential expressions. And what this allows us to do is to also introduce new instructions, things like while loops, which I mentioned before, but also early termination instructions like your breaks and continue, and even exit statements, such that if something goes wrong, maybe there's an error that you wanted to catch, you can actually now do that with exit statements. Finally, we also wanted to allow for things like local variable declaration to perform more computation as needed in a more imperative style. To give you an example, this is now something that JSONiq allows you to do. That is, for example, to compute a small function or some even inline code that, for example, computes the Fibonacci number smaller than 100. It might not be that you want to use JSONiq for this case, but for example, if you may want to fill out the table with these results and then storing it to some data lake, we imagine a future where it would be just as easy as calling some internal method where you would specify the connection to your database, and you could do it. And now side effecting was the first step to basically achieve these kind of things. Another example that I wanted to showcase, which would also just kind of explain the usability of side effecting operations, is that we can, for example, imagine situations where people, just like I mentioned, read some data from a specific JSON file. And they may want to, for example, validate some information, imagining that is some log from traffic coming through a website. They could, for example, want to know when that user verified their email, when was their last access attempt, and if there was an error or not during this verification process. So what we can do now is we can basically write functions where you can perform multiple operations in a single block of code. Like here, we can actually perform multiple replaces of values within a specific entry. And then we can also reassign values to declared variables, like we do here with the changed variable, which is initially initialized with the value of false, but we change it to a true whenever we actually find a matching user. And then we are also able to do things like early termination or just termination with a different message by using the exit returning instruction, where we can throw an error if something is wrong. For example, in this case, if we couldn't change something related to the user entry in case of an error. So what we can do with this kind of method, well, like I mentioned before, we can imagine a case where the data field would potentially read or already be some form of existing JSON representation. And we could, for example, try to count how many users we have in there. And at the same time, we may count the number of failure rates, but also we could kind of encapsulate all of this into a method that could potentially try to validate users from these logs. And then if there's an error, just exit returning a specific message so that we know we might even have some misinformation in our logs. But what I want to actually point out with all of these examples is that there's essentially an endless way in which you can try to use side effects within JSONiq, and we're just curious to see how users will now take advantages of all of these possibilities. And just to kind of give some maybe hints going forward with these changes, we imagine a world where people can do testing for different kinds of data fields and content, and also performing updates whenever they find misconfigurations. We also want to see how mutability will play a role with variables that can be declared locally and globally, and how people are going to use that in different ways. And also, like I mentioned, we want in the future to be able to store these kind of updates that happen to data directly to a data lake. So what were the big achievements that we achieved with scripting? Well, we wanted to enable imperative coding, and we were able to do so by strictly following the XQuery scripting specification, I'm sorry. We wanted to give more flexibility to users. We wanted them to be able to make use of all the functionality of JSONiq without relying on hacks that work around the current limitations. We wanted to allow for complex algorithms for different kind of use cases. We also wanted to keep it backwards compatible, such that any kind of logic that you had working before with JSONiq and RumbleDB, it still works now. We wanted to leave non-scripting code the same, so we didn't want to enforce any changes to existing syntax and semantics. And finally, we wanted to support libraries such as NumPy and Pandas directly within RumbleDB. And for that, we actually needed these changes, allowing us to perform side effects for different kind of analysis. So we'll finally go into the final segue of this presentation, which is related to NumPy and Pandas. And I guess all of you have heard about these, but in general, they provide analytical methods for multidimensional arrays and data frames. That is, NumPy is usually used for processing arrays in different kind of dimensions, computing different metrics on the data, whereas Pandas relies internally on NumPy to perform different operations relating to data frames. And they are obviously optimized for performance, large amounts of data, and we wanted to use the native versions of these within RumbleDB. However, there's quite a bit of let's say, implementation detail that unfortunately doesn't, or at least would allow us to do direct NumPy and Pandas invocation in Python, but it would just be too slow for people to make use of, especially in things like AI and ML applications. So because of that, as it's only available in Python, what we decided to do was to provide our own versions, minimized versions of NumPy and Pandas. So for that, we researched the most popular and used methods within NumPy and Pandas, and we adapted over 20 functions. We also documented the supported features so that everyone can check what we support and what is expected to work in Pandas and NumPy, and what kind of differences we have in RumbleDB. We also handle different kind of optional arguments, things like axes and so on, weren't as easy to support in RumbleDB. But where we could do so, we explicitly mentioned what kind of optional arguments are supported. And we tested it against the Python version so that we made sure that the results for the most popular methods are working as expected, and they return the same results to some specific margins of errors where there are rounding issues and so on. And yeah, like I mentioned before, we use scripting for this. So that was a very nice use case for us to see exactly how useful scripting can be in an environment where before we only had declarative ways of implementing something like this. And frankly, that would have been impossible. So just to give another example of how we can use imperative style coding now within JSONiq, we have a method here for binary search, which is used by the digitize method in NumPy. And essentially, you can, I guess, at a glance, without looking at maybe the different array access types and so on using 2 square brackets, this really starts to look very familiar to another programming language that you might use in your day-to-day use. That's exactly what we were aiming for. We believe that even someone new coming into the RumbleDB world would understand imperative style coding much easier and could also come up with better usages for their workflows by adding this functionality as well. Some of the methods that we implemented are related to things like linspace and logspace in NumPy, a range, also generating random and randomly uniform arrays. You can also compute different metrics like mean, max, median, and so on, and a bunch of different other functions, which essentially allow you now to be more analytical in the data that you actually collect from different JSONs, and to perform operations that before you probably just used Python for. And related to the pandas operations, JSONiq already supports quite a few operations natively. So we only extended that with specific methods that pandas offers, things like describe, which can provide now details about the type of data that you have inside your data frames, sample, which allows you to take random entries from your data, and so on, and the different fill and drops methods. So I'll just discuss briefly about some experiments that we've run to test this kind of implementation as well. We ran all of these on an M1 MacBook Pro with 32 gigs of RAM and 1 terabyte of storage. And we tried to run all of these tests using cold caches. We relied on the GitHub archive dataset, which is a collection of different kind of metadata corresponding to repository updates and merge requests and so on. And we also relied on some generated XML data that we converted into JSON for specific use cases. And we repeated each experiment 3 to 5 times for each data split. Firstly, we wanted to see how the RumbleDB performance changes with the introduction of scripting. And why that is because we had to make some internal changes when it comes to how things like the dynamic context works or how variables can be declared and so on. So we tested, for example, the performance of RumbleDB on a query that tries to find all the distinct logins among each event's actor and return their count. And I provided the query for anyone that's actually interested to run this as well. And as expected, the overall performance with and without scripting hasn't changed drastically. On average, we can't really feel the difference, let's say, from a user's perspective, adding just 100 to 150 milliseconds to the query. But we still, it's something that I'm going to mention towards the end. We still believe that we can get this even closer to the pre-scripting performance of RumbleDB with some additional changes that will come in the future. But overall, we are happy to say that with the introduction of scripting, we haven't degraded the user experience, and we are still providing a snappy overall query execution time for the end users. We also wanted to see how our implementations of NumPy and Pandas compared to the actual native implementations in Python. So we actually compared the describe method's performance against the Python version. And what we did is we used the event data from the GitHub archive, and we tried to scale describe on datasets of power of 2. So what we did is we ran describe on datasets that increased in size using powers of 2 until 2 to the power of 10. And what we could see was that the mean execution time was quite big, especially with smaller sizes. And that can be explained due to the nature of RumbleDB, which relies on arguments being passed by value rather than reference internally. So it takes a while to copy these values. But what is interesting is that we feel that the larger we are going to go with this data sizes, we may get actually closer to the performance of Pandas describe, because we actually get to take advantage of what RumbleDB does best, and that is working with big amounts of data. And so to end with that, what we want to do in the following releases of RumbleDB is to basically enable the interaction with external systems. We would really want to see updates to different kinds of external storage systems and so on. We also want to support more methods from NumPy and Pandas and also improve the existing ones. We want to support more optional arguments for NumPy and Pandas. We also want to be adding some different changes to our kind of segue into supporting XML within RumbleDB. And we also want to improve the performance of what we have with implementation for NumPy and Pandas, but also for the imperative style of JSONiq. And with that, I'm ready for your questions, and I'm hoping you've all enjoyed our work on RumbleDB.
Thank you, David. If nobody has a question, I have a question. I think JSONiq was originally aligned to be XQuery 3.1 without the XML bits. And I was wondering whether anybody in the RumbleDB community or JSONiq community is trying to keep up with the Qt4 community group meetings, and if there are any plans to implement XPath 4.0 functions.
So maybe I can answer this question. So hi everybody. Basically JSONiq dates back to the discussions in the working group during the design of XQuery 3.1. So that was part of the discussion. And then there were different use cases basically for the for using maps and lists in the language. And JSONiq was designed to be basically native JSON, like to be primarily dealing with JSON data. So this is why we kept it alive. But nevertheless, the intent in the end is that RumbleDB also supports XQuery 3.1, including the semantics of XQuery 3.1. We're trying to use the synergies on the virtual machine so that both of them are supported jointly. So this is the goal. And because it makes it interoperable, and we are also looking forward to also trying to implement Qt4 so at some point. But first, now we are implementing XML with XQuery 1 and then 3 and then 3.1, and then we'll see for the further steps. It's basically all a matter of resources. But as long as I have brilliant students, then hopefully we can continue to add features. Does it answer your question?
Certainly, and thank you both David and Ghislain for these lovely improvements to this tool.